Drawing Lewis structures is useful beyond indicating connectivity of atoms and molecules and polyatomic ions. We can often determine the three-dimensional shapes of chemical species from the two-dimensional images, which is an essential part of understanding and predicting their physical and chemical behavior. The process of determining the three-dimensional shape of a molecule is based on the following. Any group of valence electrons associated with a central atom will tend to orient themselves in three-dimensional space around that atom to minimize the repulsion between them. Essentially, while remaining attached to the central atom, groups of electrons such as a lone pair, bonding pair, or multiple pairs involved in a double or triple bond will position themselves as far away from each other as possible. This is the fundamental principle behind the valence shell electron pair repulsion theory, often shortened to VSEPR theory. We can illustrate this idea by looking at balloons in different arrangements around a central attachment, where the balloons represent electron groups. Just as the balloons will fill up all the available space around their center of attachment, so too will electron groups fill up the available space around a central atom. We will consider each of the 5 electron group arrangements separately. As a general notation, the central atom is A, a peripheral or surrounding atom is X, and a lone pair of electrons on the central atom is E. Regions in space occupied by bonding or lone pairs of electrons may be called domains. First, we have 2 bonding electron groups. When 2 groups of bonding electrons connect the central atom to 2 peripheral atoms, the notation AX2 applies. The surrounding atoms are as far as possible from each other on opposite sides of the central atom. The shape is linear, with the XAX bond angle being 180 degrees. The shape is the same whether the 2 bonding groups are the shared electrons in 2 single bonds, 2 double bonds, or a single and a triple bond. Looking at 3 electron bonding groups, we see that 2 shapes are possible. If all the electron groups are bonding, we have a shape known as a trigonal planar and bond angles of 120 degrees. Notice the name is planar because the 3 atoms lie in a flat plane. If one of the 3 electron groups is a lone pair, then we use the notation AX2. The lone pair of electrons can be seen to repel the bonding pairs, pushing the bonds away, resulting in a bent shape for the molecule, hence why the shape is called bent or angular. Since lone pair electrons are attracted to only one atomic nucleus, they are held less tightly than bonding electron groups. This means their electron clouds occupy more space and exert more repulsive force on the bonding electron groups than those groups exert on each other, so the bond angle is less than 120 degrees. 4 electron groups will occupy the 4 corners of a regular tetrahedron and may result in 3 different molecular shapes. If all the electron groups are bonding, then we have a tetrahedral shape with bond angles of 109.5 degrees. Note the notation used for the 2-dimensional depiction. The wedged lines are meant to show bonds in atoms coming out of the screen or page towards you, and the dashed lines represent bonds going into the screen away from you. If one group is non-bonding, we have a trigonal pyramid or trigonal pyramidal. Once again, the lone pair bonding pair interactions result in the bond angles being less than 109.5 degrees. When 2 of the 4 groups are lone pairs, then the molecule is an angular or bent shape, similar to AX2E, though the bond angles will be smaller due to the intense electron group repulsive interactions. For instance, water is AX2E2 and the HOH bond angles are closer to 104.5 degrees. Now let's look at the 4 different shapes produced by 5 electron groups. The first is when all the electron groups are bonding pairs and is called a trigonal bipyramid or trigonal bipyramidal. When 5 electron groups are present, 2 distinct sets of positions are occupied by those groups. The set of 3 positions lying in a trigonal plane are referred to as equatorial groups. The 2 positions above and below the trigonal plane are called axial groups. The equatorial electron groups are separated by 120-degree bond angles, and the axial and equatorial groups are separated by 90 degrees. If one of the electron groups is non-bonding, it will occupy an equatorial position and the shape is called a seesaw. The name seesaw comes from the observation that it looks like a playground seesaw. An equatorial position is occupied by the lone pair rather than an axial position because it has more room in the equatorial position, leading to lower electron-electron repulsion and a more stable position. If 2 of the electron groups are lone pairs, they will occupy equatorial positions. The shape is T-shaped since it looks like the letter T. If we have 3 non-bonding pairs, then they occupy all the equatorial positions and the shape is linear. Lastly, we will look at 6 electron groups. For these molecules, all 6 vertices are equivalent and point towards the corners of an octahedron. If all the electron groups are bonding, then the molecule is labeled as AX6, and the shape adopted is octahedral. All of the XIX bond angles are 90 degrees. When one of the 6 electron groups is a non-bonding pair, it doesn't matter which of the 6 locations the lone pair occupies, since all the locations are identical. The molecular shape is square pyramid. If we have 2 lone pairs, then they will be as far away from each other as possible and separated by 180 degrees, since this minimizes the lone pair repulsive interactions. Let's now try out an example. Using the information we've just discussed, it might be a good exercise to pause the video and see if you can figure out the shapes of the following molecules and assign an AXM-EN notation yourself, before we go over the answers. Alright, now we'll go over the answers. We've redrawn the molecule here with oxygen in the equatorial position, since the double bond exerts the strongest repulsive forces and wants to be as far away as possible from the other electron groups. Also, we've included more perspective by using the dashed and wedged lines for the other atoms in the equatorial positions. There are 5 electron groups around the central atom and none are lone pairs, so the shape is trigonal bipyramidal and the molecule is classified as AX5. The trigonal bipyramidal name comes from the fact that the arrangement resembles 2 pyramids stacked base to base, with 3 vertices at each base. For the second molecule, which has 6 electron groups, we've redrawn it with the lone pairs separated by 180 degrees. The shape is square planar and the molecule is classified as AX4E2. Earlier in this chapter, we looked a bit at the polarity of molecules. This is actually a consequence of molecular shape. Molecular polarity affects properties such as melting point, boiling point, and solubility, and also influences a substance's chemical reactivity in both synthetic and biological processes. We've already learned that if electron sharing in a bond is unequal enough, due to delta En, then the bond is polar. This makes determining if a 2-atom molecule is polar straightforward enough, but when there are more than 2 atoms, the shape and the bond polarities will determine if the entire molecule is polar. Let's jump straight into some examples. Starting with the carbon dioxide molecule on the top left, we see that, since oxygen is more electronegative than carbon, the oxygen-carbon bonds are polar, as indicated by the arrows, pointing from an area of lower electronegativity to an area of higher electronegativity. Due to the molecular shape, which results in the bond dipoles being exactly opposite to one another, the bond dipoles effectively cancel each other out and the molecule is nonpolar. Now would be a good time to pause the video and to try determining whether the other molecules are polar, and then we'll go over the answers. Alright, let's look at the molecule to the right of this, which is water. The bonds are polar, but this time the molecular shape is such that the bond dipoles point in the same general direction and reinforce each other. This results in a polar molecule. Turning to the molecule on the bottom left, carbon tetrachloride, we see that the molecule is symmetric, so the bond dipoles all cancel each other out. For instance, here's a molecule in 3 dimensions. As we can see, this arrangement of the bond dipoles results in a nonpolar molecule. The molecule at the bottom right, however, called chloromethane, has all of its bond dipoles pointing in the same general direction. For more clarity, let's take a look at this in 3 dimensions. The bond dipoles don't cancel and instead reinforce each other, resulting in an overall dipole moment and thus a polar molecule. These last 2 molecules illustrate the possibility that 2 molecules having the same shape and containing polar bonds could either be polar or nonpolar. Ultimately, the key question in determining polarity is, does the molecule contain polar bonds, and if so, do the bond dipoles cancel each other out or not? Using these 2 molecules as examples of symmetrical and asymmetrical molecules, we'll quickly go over some more guidelines summarizing what we've just observed. When the peripheral atoms in a molecule are identical and arranged symmetrically around a central atom, any bond dipoles will cancel out and the molecule will be nonpolar. Symmetrical means balanced or evenly arranged. When the molecule is asymmetric, which means not symmetric, either due to its shape or its composition, any bond dipoles will usually not cancel out and the molecule will be polar. Molecular polarity leads us to our next discussion topic, which is intermolecular forces. We saw earlier that opposite charges are ultimately responsible for all chemical bonds. The chemical bonds within molecules are called intramolecular forces. Intra means within. Intermolecular forces are attractive forces between ions and molecules and are usually not as strong as chemical bonds. Inter means between. It is extremely important in the AP exam to distinguish between these 2 types of forces. as students often fail to clearly explain intermolecular forces. Maybe try reciting what these different kinds of forces are to yourself a few times, or perhaps even to a fellow student, to make sure you can explain these concepts clearly. Now we'll revisit polar molecules by looking at dipole-dipole forces. These forces are attractions between polar molecules. We've seen that polar molecules each have a positive and a negative pole, so the molecules in the liquid and solid phases orient themselves so that the positive pole of one molecule will be next to and attract the negative pole of an adjacent molecule. This network of dipole-dipole forces results in higher melting and boiling points because more energy is required to overcome the attractions between molecules. The more polar those molecules are, the stronger the dipole-dipole forces. In this diagram, we use the element symbols and a dashed line to show dipole-dipole forces. The symbols above the hydrogens and chlorines, which are lowercase Greek letter deltas, indicate positive and negative partial charges, which are created due to the asymmetric distribution of electrons in chemical bonds. A special kind of dipole-dipole force is hydrogen bonds. These occur between polar molecules that contain a hydrogen atom bonded to either nitrogen, oxygen, or fluorine. The hydrogen-nitrogen, hydrogen-oxygen, and hydrogen-fluorine bonds have large electronegativity differences for a couple of reasons. For one thing, fluorine, oxygen, and nitrogen are small, highly electronegative, and have lone pairs of electrons. This allows the tiny electropositive hydrogen to get very close to the lone pairs on the partially negative nitrogen, oxygen, or fluorine atoms of other molecules. In addition, hydrogen has a low electronegativity, meaning a significant amount of electron density will be removed from the hydrogen and its nucleus will be almost unshielded. Remember, hydrogen has no core electrons. For these reasons, the bonds within the molecules will be extremely polar, resulting in particularly strong attractive forces. The attraction of the hydrogen on one molecule to the partially negative fluorine, oxygen, or nitrogen atoms on other molecules is known as a hydrogen bond. We can see the effect of hydrogen bonding by looking at this figure showing the boiling points of binary hydrides of groups 14 to 17. The group 14 hydrides in red, such as methane and silane, have low boiling points as we'd expect, since they are symmetric molecules and nonpolar. Also, the boiling points of these compounds decrease with decreasing molar mass. If we take a look at the lightest hydrides in the groups, the ones on the far left, we see something interesting. For example, examining the group 16 hydrides, the ones in green, we notice that as the mass of each polar molecule decreases, the boiling point drops, but not consistently. The boiling point of water is nearly 200 degrees Celsius more than we would expect, which is clear evidence of the strength of hydrogen bonds in water. We see a similar result when looking at ammonia and hydrogen fluoride in groups 16 and 17. Methane doesn't exhibit this trend since it can't hydrogen bond. The significance of hydrogen bonds is further demonstrated by the fact that the three-dimensional structure of many proteins, and even the base pairing in the double helix of DNA molecules, depend on the existence of these essential forces. Shown here are hydrogen bonds involving an oxygen or nitrogen atom in DNA base pairing. We will now take a look at something called London dispersion forces. Physicist Fritz London used quantum mechanics to explain this attraction. Looking at diatomic chlorine as an example, we see that the molecule is nonpolar and the electron density in the negative cloud surrounding this molecule is evenly distributed. On average, the electrons will spend no more of their time nearer one chlorine nucleus than the other. However, at any instance, there is a possibility that there may be more electron density on one side of the molecule than the other, resulting in an instantaneous molecular dipole. If this molecule is in close proximity to another chlorine molecule, then it will distort or polarize the electron cloud of the neighboring molecule. Each induced dipole results in an intermolecular attraction between the newly polarized molecules, and induces more dipoles in surrounding molecules. The strength of dispersion forces will increase as the size of the molecule involved increases, since large electron clouds are more loosely held than smaller clouds and are thus more easily polarized. Mass is an indirect indication of electron cloud volume, though it should be noted that in some cases larger mass does not mean larger volume. Take helium versus diatomic hydrogen, for example. However, London dispersion forces should never be related to mass on the AP exam. Molecular shape can play a role in dispersion forces as well. Molecules with more surface area have electron clouds that spread out and are thus more easily distorted by neighboring dipoles. For example, let's look at two geometric isomers, butane and 2-methylpropane. Both have the same overall number of electrons, but the methylpropane has a branch, meaning that its parent chain is shorter than the straight chain butane. The The methylpropane has less surface area of close contact, so it has less efficient London dispersion forces of attraction. Because of this, we would predict 2-methylpropane to have a lower boiling point than butane. Our final discussion of intermolecular forces will be about ion dipole forces. We'll focus on an ionic compound dissolved in water, for instance, sodium chloride. When the surface of the ionic lattice is in contact with water, each ion on its surface will attract the oppositely charged end of polar water molecules. This attraction between an ion and a polar molecule is called an ion dipole force. These attractive forces soon overcome those between the ions themselves, and the crystal structure breaks down. As the ions move away from the lattice surface, they immediately become surrounded or enclosed in what chemists call a hydration shell. The negative oxygen ends of water molecules orient themselves next to and surround sodium cations, while the chloride anions are engulfed by water molecules oriented with their positive hydrogens next to the ion's negative charge. While Lewis structures are certainly very useful, they have some limitations and oversimplifications. For example, we know that electrons are not accurately represented as pairs of dots in a region of space between two atoms that produce a bond. The quantum mechanical model explains that electrons actually exhibit particle-wave duality in atoms and that they are located in orbitals. The theory we'll look at now, valence bond theory, describes the location of bonding and non-bonding lone electrons in quantum mechanical orbitals, created by the overlap of standard s, p, d, and f orbitals. Hybridization is a mathematical process in which these standard atomic orbitals are combined to form new atomic orbitals called hybrid orbitals. These orbitals are located on individual atoms, but their shapes and energies differ from those of standard atomic orbitals. They are also more stable than standard atomic orbitals and minimize the energy of the molecule by maximizing the orbital overlap in a bond. Although the mathematical equations involved in hybridization are very complicated, we can just focus on some important statements that help describe it. First, the sum of the number of standard atomic orbitals is equal to the number of hybrid orbitals formed. For instance, if we have 4 standard atomic orbitals, we will get 4 hybrid orbitals. The combinations of standard atomic orbitals determine the number and energies of the hybrid orbitals formed. The type of hybridization that occurs is the one with the lowest overall potential energy. This makes sense as energy usually wants to be minimized to obtain higher stability. Finally, the electron geometry determined by the VSEPR theory, which is the material we went over earlier, can be used to predict the type of hybridization. The most common type of hybridization is sp3 hybridization, since it is found in molecules whose central atom is surrounded by a stable octet. We'll look at what is essentially the orbital diagram of carbon in methane as an example. In methane, each hydrogen has 1 valence electron existing in a 1s orbital, while carbon has 4 valence electrons, 2 existing in a 2s orbital and 2 in 2 lobes of a 2p orbital. The conversion to hybrid orbitals would look like this. The s and p orbitals combine to form 4 identical bonding orbitals, designated sp3. Note that it is written here as 2sp3, which is more specific since it indicates the principal quantum number, but sp3 is fine as well and is generally more common. Each of these hybrid orbitals can share their electron with 1 hydrogen atom. An sp3 hybrid orbital resembles a p orbital with an enlarged end. So what we have here is 1 spherical s orbital and 3 figure-8 shaped p orbitals, 1px, 1py, and 1pz, combining to form 4 identical sp3 hybrid orbitals. This is typical of a tetrahedral arrangement with all bond angles approximately 109.5 degrees. Some notes on hybridization. Hybridized orbitals can hold lone pairs or bonding pairs. We'll see this in some examples later on. We call the region in space occupied by a pair of bonding or lone electrons, regions of high electron density, a domain. As mentioned earlier, lone electrons exert greater repulsive forces than bonding electrons. There are more types of hybridization to discuss, but we must first turn to the situation that we have a double or triple bond. Single bonds, such as those in methane, are known as sigma bonds. In brackets here we have the lowercase Greek letter sigma. This type of bond occurs when 2 atomic orbitals combine to form a covalent bond that lies along an axis connecting the nuclei of the 2 atoms. If you don't understand the statement about the axis yet, don't worry. We'll look at an illustration to clear things up soon. In double bond formation, there is an overlap between 2 hybridized orbitals called a sigma bond overlap, and the overlap of 2 unhybridized p orbitals. This is called a pi bond overlap, denoted by the Greek letter pi. A double bond consists of 1 sigma and 1 pi bond overlap. Okay, to actually get a sense of what this means, we need to look at a depiction of this in 3 dimensions. This is a molecule of ethene, and for now we're only looking at the sigma bonds. Between the two carbon atoms, we have a sigma bond, formed by an overlap of px hybridized orbitals along an axis between the two atoms. Now we'll just take a look at the pi bond, which is formed by an overlap of py orbitals above and below an axis between the carbon atoms. These p orbitals do not participate in the hybridization and are not directed along the axis between the carbons. Superimposing these, we see the complete depiction of the double bonded molecule, with the one sigma bond and one pi bond between the two carbons. It's important to note that in the determination of molecular shape or hybridization, we must think of a double or triple covalent bond as occupying one domain only. This makes determining hybridization pretty straightforward, since pi bonds don't undergo hybridization. Multiple bonds are often associated with sp or sp2 hybridization. For instance, when one spherical s orbital and one figure 8 shaped p orbital are combined, two sp hybrid orbitals are formed. We still have two p orbitals left on each sp hybridized atom, which participate in pi bonds. Don't worry if you're unsure of how to identify these types of hybridization yet. We'll go over some examples after this slide. There are two other types of hybridization we'll go over, though they are currently not being assessed on the AP Chemistry exam, at least at the time this video was released. In third period elements, the 3d orbitals are so close in energy to the 3s and 3p orbitals that the hybridization of one s, 3p, and 1d orbital results in a trigonal bipyramid geometry. This is sp3d. The formation of sp3d2 hybrid orbitals in an octahedral array can be accomplished by the hybridization of 1s, 3p, and 2d orbitals. Here we must determine the hybridization of the central atom in each of these structures. Before going over the answers, it might be good practice to pause the video and try determining the hybridization yourself. You could also determine the shape of each molecule. Alright, here are the molecules redrawn to depict their shapes, with the names of the shapes written below them. Next, we'll go over the hybridizations. Starting with the molecule at the top left, we see that it has 4 electron domains circled in yellow. This indicates 4 hybrid orbitals, so the central atom is sp3 hybridized. To the right of this, we have boron trifluoride, which has 3 electron domains, making the hybridization sp2. The molecule further to the right has 5 electron domains since the double bond counts as only 1 electron domain. In this case, it is sp3d hybridized. Notice how the number of electron domains equals the number of hybrid orbitals. Here we have 5 electron domains, and sp3d hybridized means we have 5 hybrid orbitals. Moving on to the molecule on the bottom left, we see that there is a triple bond and a single bond around the central atom. This means there are 2 electron domains and the hybridization is sp. To the right of this, we have a water molecule. Recall earlier when we said hybridized orbitals can hold lone pairs or bonding pairs. The 2 lone pairs and 2 bonding pairs on this oxygen atom result in it having 4 electron domains. Thus, the hybridization of the central atom is sp3. The molecule to the right of this has 6 electron domains and is sp3d2 hybridized. Our last topic of discussion will be formal charge. This is an entirely fictitious charge that is used to defend the most probable Lewis structure of a molecule when several different Lewis structure arrangements are possible. The formal charge on an atom in a molecule is the charge each atom would have if all bonding electrons were shared equally between the bonded atoms. One way to calculate the formal charge of an atom is to subtract the number of lone electrons and the number of bonding electron pairs around it from its number of valence electrons. We can simplify this method if the Lewis structure is drawn. In this case, the formal charge of an atom is just equal to the number of valence electrons minus the sum of dots and lines. The following rules apply to formal charges. First, the sum of all formal charges in a neutral molecule is equal to 0. If we have an ion, then the sum of all formal charges must be equal to the ion's charge. Small or zero formal charges on atoms are preferred. Be aware, however, that this statement has been questioned by bonding theorists lately, since a structure that satisfies the octet rule may be more likely than one in which formal charges are minimized. The final rule is that the preferred structure will be the one with a negative charge on the more electronegative element, given we have a structure with atoms with a non-zero formal charge. As a side note, please remember that formal charges are not actual charges. They don't produce electronegativity or polarity in a molecule, and are simply used to assist us in determining which is the most likely structure out of a selection of Lewis structures. Now for an actual example. Here we are asked to draw 2 possible structures for hydrocyanic acid and indicate which structure is preferred based on minimizing formal charge. We've already gone over drawing Lewis structures in a previous video, so here we'll just draw the only 2 possible structures. You might observe that based on what we discussed earlier, we would expect carbon to be the central atom, since it has a lower electronegativity than nitrogen, but we'll just keep that at the back of our minds for now. Looking at the left structure, we'll first calculate the formal charge of hydrogen. The number of valence electrons of hydrogen is 1. We have no dots and 1 line, or in other words, no lone electrons and 1 bonding pair of electrons. So we subtract 0 plus 1 from the 1 valence electron. You might choose not to include the 0, it's just done here to be extra thorough. Next to the hydrogen atom, we can draw a circle around the formal charge, which is how formal charges are generally shown. Moving next to nitrogen, we subtract 4 from 5 because we have 5 valence electrons and 4 lines or bonding pairs around the nitrogen. It has no lone pairs. We end up getting a formal charge of positive 1 on the nitrogen. The carbon has 4 valence electrons and 2 lone pairs and 3 bonding pairs around it, so it receives a formal charge of negative 1. If we carry out a similar procedure for the structure on the right, we see that all the formal charges are 0. Note how the formal charges of both structures add to 0, agreeing with the total charge of the molecule. If this wasn't the case, it means we must have made a mistake somewhere. Clearly, the structure on the right has the minimized formal charges. Maybe more specifically, the magnitudes or absolute values of the charges are minimized. So we predict that this structure would be preferred. As another quick example, we need to determine which of these pre-drawn structures is preferred based on minimizing formal charges. Once again, this is a good time to pause the video and to try and make the determination yourself before seeing the final answer. We'll skim over the calculations of the formal charges, though it's still shown here and is exactly the same procedure we used in the previous problem. Notice that both structures have formal charges of -1, 0, and +1, so we need to look a bit closer at them to determine which is more stable. Remember our rule that the preferred structure will be the one with a negative charge on the more electronegative element. Oxygen is more electronegative than sulfur, so the molecule on the left, where oxygen has the negative formal charge, is the one that's preferred. By the way, this is the actual structure of this molecule, called carbonyl sulfide, though the problem doesn't ask for this. This structure actually has formal charges of 0 on all the atoms. You can check for yourself if you'd like.